In the last video, we talked about the relationships between pressure, volume, temperature, and number of particles, mainly pressure as it relates to these other three. In the past, we've also talked about the relationship between temperature and volume. So keep those in mind also. So if you remember, we said that things expand when they get hotter, and so volume and temperature vary directly. As temperature goes up, the volume's going to increase. And with gases, that is a proportional relationship. So there's one more relationship that we're going to keep up with. Now, there is an equation for what we're going to do, and you can watch several videos online that show you how to do this with the equation, but this is just a way to set these up that I think makes it a little bit easier. And what I like about this is you actually have to think about the relationship. It's not memorizing an equation and plugging into it. It's about really understanding what's going on in the problem and with these relationships. So you're going to be solving several problems like this, and so I'm just going to go through several examples with you of PVTn problems. So the first one here says your full car tire. And so let's say that a full car tire has 100% of the air that it can hold, and we don't really have a good way to talk about the number of air particles. We're not going to count them out, and eventually we will. We'll start talking about something called the mole, but we're not there yet. So right now, let's just say we're going to call that the number of puffs of air, and each puff has some number of air particles in it. Every puff has an equal number of those air particles. So let's say 100% is 100 puffs. And so in that car tire, you've got a pressure of 31.2 pounds per square inch. So your tire begins to leak. Bad news. After the tire loses 15% of the air, or 15 puffs, what is the new pressure? So we're going to set up a little chart. We call this a PVTn chart. And I didn't write this in. We've got the variables across the top. And then down the side here, we're going to look at these relationships. So we're going to look at what we have at the beginning. We call that the initial. We're going to look at how that's changed. We're going to call that the final. And then this is the key. We're going to look at the effect that these changes have. So with this one, we're talking about the number of particles and the pressure. It doesn't say anything at all about the temperature, so I'm going to mark out that column. It doesn't say anything about the volume. Now, the volume of the tire may change a little bit as it leaks, but it's pretty much going to hold its shape unless it gets really, really flat. So we're not going to worry about the volume change in this one either. So I'm going to go ahead and mark out those columns, because if nothing changes from the beginning to the end, there's really no effect on the other variables. And so for these first two problems, we're going to focus on one thing at a time. All right, so I'm going to look at the pressure, and it tells me that at the beginning, the pressure is 31.2 psi when I have 100 puffs of air. So I'm going to fill that into my chart. I have 31.2 psi. Doesn't matter what pressure you use as long as your pressures all match. And the number of particles here is 100 puffs. So I'm just going to fill in what I know. So this is the final situation. After the tire loses 15% or 15 puffs, so actually they don't give me the number I need, but if I started with 100, I lose 15, I've got 85 puffs left. That's my new number of particles. And the question is, what is the final pressure? So I'm just going to put a question mark there. You can leave that blank and put your answer there if you want to, but whatever. Doesn't matter. This is the key, and this is where your understanding of those relationships comes in. All right. So what happened to my number of puffs? I went from 100 to 85. So the number of puffs decreased. It went down. I'm going to draw an arrow pointing down. And then what is that relationship? If I have fewer puffs, fewer air particles in there, I'm also going to have less pressure because I'm going to have less collisions of the particles with the sides of the tire, the inside of the tire. And so I'm looking for a decrease in pressure. Now, this is where it's a little bit confusing. When I set up my calculation, I always use the arrow or arrows, sometimes two things can change at the same time, that's underneath my question mark. I'm always going to use the one that's underneath what I'm looking for. And I'm going to basically use a factor of how much this has changed. So I'm going to start with the pressure at the beginning, 31.2 psi, and I know that the pressure, sorry you can't see it, I know that the pressure has to go down because I've got fewer particles, I'm going to have less collisions, less pressure. So I have to set up the ratio of the number of particles so that when I do the math here, the pressure decreases. So if you think about what's going to make this number smaller, it's going to be multiplying by a fraction that's less than 1, right? So what I'm going to do here is I'm going to put the bigger of these two numbers on the bottom and the smaller number on the top. So the unit of measurement of puffs cancels out, and I'm going to get a pressure there in psi. So doing the math, I've got 31.2, and just like doing a conversion anytime, I'm going to divide by what's on the bottom, so divided by 100, and I'm going to multiply by what's on top. And I'm going to get 26.52. So I'm going to pretend that that's exactly 100 so I can keep my sig figs. This has 2 sig figs. I'm going to round that to 27 psi. And so there is my answer. Now, make sure it makes sense. I said that the pressure needed to go down. I went from 31.2 to 27. So the effect is that the pressure went down. Now, if this number had been higher than 31.2, I know that I've got this set up the wrong way. I'm going to flip it over. So use your brains there and make sure that you have it set up correctly. Now, the other thing I'm going to tell you here, just sort of a little mental shortcut, is when I look at this arrow, what we always say in class is the arrow is going to point to where the big number goes in the fraction. So if I need the number to get smaller, the big number goes on the bottom. If I had a problem where this went up, I'm going to put the big number on top. So if you can kind of remember that the arrow points to where the big number goes, you've got this. All right, let's do another example. In this video, we may have to switch videos before we get through all of our examples. So here's one more. It says a helium balloon, or when a helium balloon is filled inside of the store, its volume is 4.32 liters and the temperature is 23 degrees Celsius. What will be the volume of the balloon when you take it outside where the temperature is 33 degrees Celsius? So, PVTn. It looks to me like I've got volumes here in liters and temperatures. So right now, I'm going to cross out these others. Sometimes it'll say pressure remains constant, the number of particles remains constant, the balloon's not leaking. So I can mark out the ones that I'm not dealing with in this problem. The initial volume is 4.32 liters. And here is something that you have to pay attention to, and that's the temperature. So if you remember this little graph that we did in the last video, we said these temperatures are only proportional to each other if I use Kelvin temperatures. So I can't use Celsius in my PVTn charts. I have to use temperatures in Kelvin. And you need to know how to convert that. It's really simple. So for Celsius to Kelvin, you're just going to add 273 to the Celsius temperature. Celsius and Kelvin degrees are the same size. It's not like Fahrenheit and Celsius that the degrees are actually different. The Kelvin scale is just shifted downward 273 spaces. So if I've got a temperature of 23 degrees Celsius, I add 273 to that, and that gets me a temperature of 296 Kelvin. Never, ever, 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 ever put a Celsius temperature in your PVTn chart. Always convert it to Kelvin. So 296 Kelvin. Otherwise, it's not going to be proportional. All right, you take it outside, it's a hot day, the temperature is 33 degrees Celsius. So 33 degrees plus 273 is 306 Kelvin. Sorry, you couldn't see any of that I just wrote down. 33 plus 273, there's your answer. By the way, we don't say degrees Kelvin. I don't really know why, but it's just 306 K, no degree sign. And I'm looking for the new volume. That's my question. So this is one, again, that we didn't really do in the lab, but we learned about it in the previous unit where we talked about state changes and expansion and contraction. So my temperature has gone up. When temperatures go up, the volume increases. And like we said, always look at the arrow that is underneath what you're trying to figure out. This is the one that tells you what to do with these numbers, and that's what's a little confusing about this. I know what these numbers did. This tells me what I have to do. So I'm going to start with what I'm looking for, which is a volume, 4.32 liters. This volume is going to increase because of the temperature increase. So the bigger of the two numbers goes on top. The smaller goes on the bottom. Remember, the arrow points to where the big number goes. It's a little cheat there. So 4.32 times 306 divided by 296 is 4.4659. Everything has 3 sig figs, so 4.47. And Kelvin cancels out, so this is a volume in liters, which is what I want. And again, make sure that your units make sense. Make sure your answer makes sense. So my units canceled out like they should. I said here that the volume needs to go up. 4.47 is greater than 4.32. And so that's just one more check that I can do to make sure that, that I did the math correctly on this. All right, that's about it for this video. I'm just going to keep doing examples. And so I think you do want to watch, or I know you do want to watch the next video to see what to do if you've got more than one variable changing. But again, if you see one of those and you feel like you're ready to move on, then by all means move on, start those practice problems. You can always come back and watch more examples if you get stuck somewhere. So that is it for this video, and I will see you soon.